All right, Unit 7, Stoichiometry. Today I am going to go over the Section 1 of Unit 7, which are mole-to-mole conversions. There are some practice items within these slides, so if you don't need me to go through, well, review practice items. Some of the stuff like, for example, here we have, practice balancing equations. If you don't need that, just, fast forward. Actually, I think I'm just going to annotate straight on the screen. Let's try that, see if it works. Okay, so we're going to balance this equation. They just want to know moles of oxygen, but you kind of have to balance the whole thing. So again, just do your little chart. You have the reactants and the products, of course, that must balance. And we have carbon on the reactant side. There's 2 of those. We have a hydrogen. There's 4 of those. And oxygen, there's 2. On the product side, we have 1 carbon. For hydrogen, we have 2. And for oxygen, there are 3. Okay, so let's go ahead and try to get our carbon straight. We have 2 on the reactant side, but we only have 1 on the product side. So let's put a 2 in right there. And that is going to change your carbons to 2, but it also changes your oxygens as well. So now you have 4 oxygens there plus your other one over here. So that's going to give you 5 oxygens. All right, second, let's fix our hydrogens because we have 4 on the reactant side and only 2 over there. So let's put a 2. It's going to let me move this out of the way. Put a 2 right here. Okay, that's going to be 4 hydrogens. We had 2. 2 times 2 is 4. And that is going to increase your oxygens. We now have 4 oxygens right here with the CO2, and we're going to have an extra 2 there. So that's going to increase our oxygens to 6. So now we have the carbons balanced. We have the hydrogens balanced. We got to fix our oxygens. This is the last thing. We have 2 on the reactant side. That's an elemental, which means it's all by itself, which is what they were asking for in the first place. And in order to get this 2 up to 6, we're going to need a coefficient of a 3 right there, which is going to turn that into 6. So your answer is letter C for that problem. All right, let's look at number 2. Number 2 says the subscript of oxygen in the product should be. Well, this one's fairly easy because look what you have here. You have on the reactant side, you have 2, and you have a 5 here as a coefficient. So that means you have 10 oxygens on this side. Well, we got to make 10 oxygens over here too. You have the 2 here. So what number do we have to put here to make 10 on this side? 2 times what is 10? That would be a 5. So your answer is G. All right, and number 3, this one's asking you about how many moles. So let me clear the screen. And let's take a look at this. Okay, so what you got to remember for this one, remember 1 mole of anything contains 6.022 times 10 to the 23rd molecules. Okay, so they're telling you that you have this many molecules, and we're trying to see how many moles we have. Okay, well, we have this many molecules. We got to see how many times 6.022 times 10 to the 23rd. We'll go into that. So basically what you're doing, and make sure you put your parentheses around these scientific notations because calculators act weird sometimes if you don't do that. So this is how many molecules we have. And we know that every mole has got this many molecules in it, so we got to divide. Okay, when you put all that into the calculator, you should end up with 3.39 moles. Okay, again, just make sure you put those parentheses in around your scientific notations. All right, moving on to the next. Actually, that should have cleared first. How about we clear out, please? Clear my drawings. Okay. And moving on to our next page here, number 4, in our checks for understanding. When this equation is balanced, the coefficient in front of our H3PO4 is, okay, so we're going to have to take this out and balance it. I know it only asks for one. You kind of have to do the whole thing. All right, so let's take a look. Again, this is our reactant side. This is our product side. We have calcium. There's one of those. Now, look what we have. We have a polyatomic ion. And remember, I told you, as long as they keep them together, you can keep them together when you're doing this part. So they stay together on the reactant side, and they're staying together on the product side. So we have 2. A little 2 right here. And then we have H. And there's 3 of those. And then we have another polyatomic ion right here, PO4. And look, PO4 is kept together on that side as well, so we can keep it together when we're doing our count. So there's 1 PO4 on the reactant side. All right, let's do our product side. Calcium, we have 3. And our NO3, there's only 1 of those. For hydrogen, there's only 1 of those. And then for PO4, if you look, you have a subscript outside the parentheses there, so you have 2 of those on the product side. All right, what do we want to do first? Let's take care of calcium first. It doesn't really matter, but let's take care of calcium first. And you can see there's only 1 on this side where we have 3 on that side. So let's put a 3 in front. That's going to change your calcium to 3. But it's going to change your NO3 to 6 because you have 2 on the outside, so 2 times 3 is 6. All right, what do we want to look at next? Let's go with, I guess, trying to fix our NO3 now. So you have 6 NO3s on the reactant side. We only have 1 over here, so we need to put 6 right there, which is going to change the NO3 to 6. But it also changes our hydrogen count to 6. Okay. Let's see, and now I guess we need to fix the hydrogens, and we need to fix the PO4 counts. So hydrogen, there's a 3 right here. In order to make that a 6, because this is going to turn into a 6, if we put a 2 here, that will change that to 6. Now, does that fix our PO4? It sure does. It turns that into a 2. So now everything is balanced, and the answer to your question there, for the H3PO4, they wanted to know what coefficient goes in front of it. Boom, there it is. All right, checks for understanding number 5, how the number of molecules in 48 grams of oxygen gas is. All right, let me clear my screen so I have room to write. Okay, so what you're doing, you're being given the grams. Okay, so we have grams. And then they want us to go to molecules. Well, remember, 1 mole is equal to 6.022 times 10 to the 23rd molecules. So we need to figure out number of moles. So this is kind of a 3-step. So we have to take it grams to moles, and then moles to molecules. All right. So we got to figure out how much oxygen gas weighs. We take their molar mass, so we can figure out the number of moles. And of course, oxygen is a 16 on the periodic table for our atomic mass, but there's 2 of them. So O2 is equal to 32 grams per mole. All right, so how do we figure out? We're going to go from grams to mole. They've given us 48 grams, so always start with what you're given. 48 grams of O2 times 1 mole of O2 equals how much do we say? Right here, 32. Okay, so that way we can cancel out our grams here. And what you're going to end up with is 1.5 moles. So that's how many moles are in 48 grams. All right, now we have to take the moles and go to molecules. So now you're going to take 1.5 moles. And what did we say? How many molecules are in each mole? We said 6. 0.022 times 10 to the 23rd. Okay, put that into your calculator, and you should end up with 9.03 times 10 to the 23rd molecules of O2. All right, your answer is right here. Okay, like I said, multi-step, but you know, look at, see what you're given, see where you got to go, and kind of work it from there. Okay, clear the screen. All right, guys, I'm going to skip through all these, go over them in class basically. I just want to make sure y'all had the worked out examples. Okay, so this is kind of new, but this is pretty easy stuff. This part is anyway. So what we're looking at here is let's look at ratios. Okay, so here's your equation. And remember, we're going to be looking at the coefficients that are in front of these molecules for the ratios. All right, the first ratio wants to know N2. All right, so N2, there's nothing in front of it, so we know that's 1 N2 to every how many H2s? 3. Okay, so that's how you do that. Now, this will come into play later for us figuring out some other stuff. Right now, you're just trying to figure out ratios, mole ratios. All right, now letter B wants to know how many N2s. N2s, we said there's no number in front of it, so that indicates there's only 1 N2. And that wants to know for every 1 N2 that you have on the reactant side, how many NH3s, or how many products do you get? Oh, there's 2 there, so you're going to get 2 NH3s produced for every 1 nitrogen molecule or compound. All right, and then letter C, I want to know the number of hydrogens per product. So you get 3 H2s, and for that, you still get 2 NH3s. Okay, so these are your ratios, 1 to 3, 1 to 2, and 3 to 2. Sometimes I will go ahead and write out so I don't mix up, you know, which, you know, ones I'm talking about, and that's fine if you want to do it that way. All right, now this one, this is our equation we're looking at here, and again, you're looking at these coefficient numbers that are in front of each one of these molecules or compounds. All right, so first one wants to know how many H2s we have. There are 8 moles of H2, and wants to know how many products we get for each one of those 8 H2s. Well, look, there's an 8 there too. So it's 8 to 8. So basically, you can reduce this. It's a 1-to-1 ratio. Okay, so whatever number of hydrogens you have, you're going to get pretty much the same amount of your product there. All right, now they want you to compare the hydrogens to the sulfurs. So hydrogen and there's no number in front of that, so we know that's a 1 to every 1 sulfur. And then H2S, now we're looking at the product, 8 H2S's to every 1 S. I guess I should put the 8 there. I'm not putting the 8 as a subscript, but all right. So again, these are fairly easy. You're just looking at the coefficients in front of the compounds and for the whatever, you know, that they're looking for. All right, so the answers are here. If you need to go back and take a look. I'm going to skip over our grilled cheese sandwich and let's look at our mole to mole ratio, example 3. All right, so we have 3 hydrogen gases, remember the diatomic molecule, to every 1 nitrogen, and that's going to give you 2 ammonias. So they want to know how many moles of nitrogen are needed to react with 9 moles of hydrogen. Okay, wow, so now they're changing some numbers up on us. All right, so what you need to do first is how many moles of nitrogen are needed. Let's take a look at the ratios, okay? So we are looking at nitrogen. Actually, if I could get my annotation tool to work. There we go. So we're going to look at, because they're asking about nitrogen and they're asking about hydrogen. So normally, look, we have 1 nitrogen to every 3 hydrogens. All right, so now what do they have? They want to know how many moles of nitrogen are needed to react with 9 H2s. So look, we normally have 1 to 3, and now we've gone from we don't know what it is to 9. Well, you can do this in your head. I'll walk through the steps. It's really just kind of a cross multiply kind of thing. Hopefully you can figure it out, but let me walk through the steps. Okay, so let's look at our ratios. Normally we have a 1 to 3 ratio, and now we're trying to figure out this new ratio. And we don't know what X is, because X is the new number of moles for nitrogen. Okay, so this is what the reaction normally tells us we have, but now we've bumped up our number of hydrogens that we have, and we're trying to figure out how many that. So you just cross multiply. So 3 times X is 3X, and that 9 times 1 is 9, and then you just solve for X. X equals 3. So we need 3 moles of N2 to react with those 9 moles of hydrogen. Okay, clear this out. Moving on to part 2, or letter B. How many moles of NH3 will be produced? Okay, so this is where they're asking with this scenario here, where we just said we needed 3 of these, so 3 of nitrogen and 9 of that. So normally, let's take a look what we normally have. We are normally having, and we can pick, I guess since we just calculated this, pick one of your reactants, doesn't matter which one. But since we just did the 3, let's go ahead and go with that. So we normally have 3 N2s give us how many ammonias? 2. All right, so that's our normal. Well, not our normal, but that's how it is in this lowest form. But now they want to know if, oh, sorry guys. Normally we only have 1 there. Let me back up. Okay, 1 nitrogen to 2 ammonias. But remember, we're bumping it up to the 3. So now we have 3 nitrogens. And we want to know how many of these guys we're going to get. And you could do this with the 9 moles of H2 as well. In fact, I'll show you it comes out the same. So in a case like this, we could just, pick whichever reactant we want. But we'll do both of them. So we know we have 9 moles of H2. And again, we want to figure out. You only have to do one of these. Okay, you pick. But I'm going to do both of them. All right, so this is what we normally have. 1/2 ratio, and now we have 3/x. Okay, so 1x, 2 times 3 is 6. Okay, so we're going to get 6 NH3s. But again, we can let's look at this one so we get the same answer. Now we're looking at what do we say? We normally have 3 H's to every 2 ammonias. And now we have 9 H's, and we want to know how many ammonias we're going to get. 3x equals 2 times 9 is 18. Divide by 3. 3 goes into 18. Hey, look, 6 times. So you're going to get the same answer both ways if you do it right. It doesn't matter which reactant you use to figure it out. So I just want to show you that. It's all about the mole ratios. That's all you're doing, and then cross multiplying. All right, let's get rid of this. Move on. There's our answers. All right, let's look at example number 4. All right, is this reaction usable as it is written? Okay, unfortunately in chemistry you don't always be given chemical equations that are balanced. So sometimes we have to balance them before we can do anything. So let's take a look. we'll do this part first and see if it is balanced. So the reactant side, the product side. All right, we have 1 C, we have 4 hydrogens, we have 2 oxygens. On the product side, we have 1 carbon, we have 2 hydrogens, and we have, what, 3 oxygens. All right, so let's throw a 2 here in front of our hydrogen or water, and that's going to change that to 4, but it's also going to change our oxygen count too. So that's now 4 oxygens. All right, and how are we going to fix the oxygen? Well, that's pretty easy because it's an elemental on this side. We just got to change that into a 4, or make it into a 4. So what do? You put a 2 in front of it. 2 times 2 is 4, and now it's balanced. Okay, so no, it was not usable as it was written. We had to change some, I'll put some new coefficients in. Okay. So I don't want to clear the whole screen because I want to leave my coefficients in there. I guess it probably would have been easier for me to clear the screen and just rewrite the 2's, but oh well. All right, how many moles of oxygen are needed to react with 0.5 moles of CH4? All right, so what are we looking at? We are looking at the oxygens and the CH4s. So what is O2? We have 2 of those. And then CH4, there's no number in front of that, so that tells us there's a 1. So 2 oxygens to every 1 CH4. All right, so it says how many moles of oxygen. So we need to figure out when we have 0.5 moles of CH4. Well, take a look at it. We have basically halved what CH4 is normally, so you would have to halve that. But I'm going to walk you through it, how you would do it mathematically. So this is a 2 to 1 ratio, and now we're trying to figure out what it would be if we changed. So we're trying to figure out oxygen. That's why we put the X here. That's our unknown, and this is our new 0.5 is our new moles for CH4. All right, so X times 1 is X, and then 2 times 0.5 or 2 times a half gives us a 1. Okay, so our answer for that is 1 mole of O2. Okay, so this is letter B. All right, and C, they want to know how much water can be produced from half a mole of CH4. All right, so let's take a look at what we normally have for CH4 compared to how much water we normally get. So CH4 again is 1 CH4 gives us 2 waters. All right, but they've changed it. Now they're telling us we only have half a mole of CH4. And we're trying to find out the new amount of water. All right, so that's 1 over 2, and then we have 0.5 over X. X times 1 is X, and then 2 times 0.5 is 1, so we're only going to get 1 mole of water. Okay, so that's the answer for C. All right, so that was pretty simple. Most of y'all can do that in your head, but I just wanted to walk through the process with you just in case. Okay. All right, checks for understanding. Number 6, how many moles of carbon dioxide are produced when reacting 6 moles of butane in an excess of oxygen? When they say excess of oxygen, that means you have more than enough, so you don't really have to worry about, running out of oxygen. All right, so let's take a look. All right, for this one, let's take a look at what we're looking at. We need to look at the ratios of CH4 and CO2. So CH4 and CO2. So CH4H10, and look at me, I can't write. That should have been H10 to the ratio of CO2. All right, so we have for every 2 of these, we're going to end up with 8 CO2s. All right, how many moles of carbon are produced when reacting with 6 moles of butane? So now we're changing it to 6, And we're trying to figure out what our new number for CO2 would be. So 2 over 8 equals 6 over x. Do you cross multiply? 2 times x is 2x. And 6 times 8 is 48. You can divide by 2 so you can solve for x. Okay, you're going to get 24 moles of CO2. There's your answer right there. Number 7, how many moles of hydrogen gas? Now we're looking at this equation. So we're looking at hydrogen gas. So there's your hydrogen are produced when you have 0.066 moles of sodium. Here's your sodium right here. So what do we have? Normally our sodium is usually 2 moles to every, there's no number in front of H2, so that's 1. So it's a 2-to-1 ratio. And they're telling us that we only have this much or this many moles of sodium. And we're trying to figure out how much H2 we will get. Okay, so that's basically 2 over 1 equals 0.066 over x. Okay, so that's 2x equals 0.066 divided by 2 to solve for x. And you're going to end up with 0. X is equal to 0.033 moles. And there's your answer right there. Okay. Clear this out. Move on to the next. All right, checks for understanding number 8. A lot of words in this one. Phosphoric acid is used to neutralize magnesium hydroxide according to the equation shown. How many moles of water, so we're going to be looking at water, will be produced from the neutralization of 0.24 moles of phosphoric acid? All right, so we got to look at the ratios of those two. So H3PO4, there's normally 2 of those. And how many waters do you get when you have 2 of those? 6. All right, so now they're telling us we only have this many moles of H3PO4, and they want to know how much water will be produced with that. So set it up, 2 over 6 equals 0.24 over x. This is going to give you 2 times x, and 6 times 0.4 is going to give you 1.44. Divide by 2 to solve for x. X is going to equal to 1.72 moles of H2O. And 0.72, is that what I said? I think that's what I said. I wrote it. 0.72 moles. Okay. Clear the screen. Actually, I'm just going to go clear all. All right. Now we're going to look at a combustion. And you know it's combustion because you got your oxygen right here, and you got your CO2 and water that are being produced on the product side. All right. Butane, how many moles of water? So we're going to be looking at water. Here's your water. Produced by 12.5 moles of butane. So now we're comparing butane to water. So what do we normally have? C4H10. We have 2 of those to every 10 waters. There's your 10 and your 2. But now they're telling us we only have 12.5 moles, so we have a lot more. 12.5 moles of that, and they want to know how much water we're going to make. Set it up. 2 over 10 equals 12.5 over x. 2 times x is x, 2x equals, and then 10 times 125. I'm sorry, 10 times 12.5 is 125. Solve for x. Okay, so we plug that into your calculator. You're going to get 62.5 moles of water. And 62.5 moles. There it is. All right, one more, I believe, in this section. Got some particle sketches. You can go back and read about those. Really, technically, you have to make sure that you have the right numbers. None of this time you're looking at pictures, okay? So look and see what we've got. You kind of have to write out the equation for this one so you can visually see it and make sure it's balanced. I guess that's the main part. Balance the equation before you can do this. All right, so we have, let me get my writing tools up. Again, y'all, this whole writing equations thing, or at least balancing them, is a big deal. So we have N2 plus H2, let me tell you right here, combined to form ammonia. NH3. Now, before we can do this, we have to make sure it's balanced. Reactant side, product side, we have two hydrogens, two nitrogens, and then for on the other side, you have one nitrogen, but you have three hydrogens. All right, so let's put, let's see, the easiest way to do this. Let's go ahead and fix our nitrogens. There are two there. That gives us, actually, no, we can't. Guys, this one's kind of, this is where I told you if you screw up, you can go back and you might have to fix it. This is one of those ones you kind of have to look ahead, because you're going to have to put a coefficient in front of this NH3. And the reason being is if you try to fix your nitrogen, it's going to mess up the other two. So anyway, let's go ahead and do that. 2 times N is 2, and 2 times H, that makes that 6. And then, well, I guess it's not what I was thinking. Never mind. I don't know what I was thinking. And we're going to put a 3 here. And then that turns into 6. So that now balances this equation. Miss Taylor was thinking of something else. Never mind. Okay, so that wasn't hard. All right, so what are we looking at? We are looking at, for every one of these, they're giving you just the N2s and the H2s. So let's look at a ratio. For every one N2, you're going to end up with 3 H2s. So do you see something that gives you that? I don't see anything in there. The N2s are the white ones. Okay, and there is no one of anything. There's multiples of each. So when this happens, you just bump up the ratio. Okay, let's bump this up, multiply everything by 2. So 2 times 1 is 2, and 2 times 3 is 6. So let's see if this ratio works, 2 to 6. All right, do you see anywhere where you have 2 nitrogens and 6, 2 nitrogens and 6 hydrogens? Okay, I see 2 nitrogens here, but there's only 1, 2, 3, 4, 5, so that's not going to work. I see 2 nitrogens here, 1, 2, 3, 4, 5, and there's 6 hydrogens. So here's your answer, guys. So again, this is a ratio thing, but sometimes the ratios are bumped up because, you know, the numbers at least. It's still the right kind of ratio. It's just there's going to be multiples. All right, so that's the answer to that, letter D. All right, guys, that's section 1. Everything worked out for you. If you have questions, please email me or talk to me in class. Have a good day.